Okay, test test one, two, three. My audio looks good. So welcome to another video in the Python for DevOps series. Unfortunately, the last video I was troubleshooting, trying to follow along with the Flask by example tutorial. Um, I've been doing a tutorial on real Python, the Flask by example series. And I've had so let's take a look at that a little bit more closely. So I was implementing a task redis queue on there. Uh, so but I was having problems with that. I couldn't get the database to populate with values. There was a problem with the insert statement. And I just had a heck of a time. I was kind of hoping to just go through and have everything work and kind of have a good kind of fun experience, but it turned out to be nothing but frustration for me. And it turned out to be a lot more time consuming than I thought it would be. So unfortunately, I think what I want to do in this next video is just move on from this. I've talked about this on the channel before. I call it taking an L. It sucks to take an L. It sucks to lose, but there's something called a Pyrrhic victory. We'll look that up. So Phyric, I think is called. Yeah, I'm not sure how it's pronounced, but I pronounce it Phaeric. A Phaeric victory is a victory or success that comes at the expense of great losses or costs. In business, examples of such a victory could include succeeding at a hostile takeover bid or winning a lengthy and expensive lawsuit. So I like to avoid those whenever possible. In this case, I think really struggling, spending hours and hours and hours, and getting this tutorial to work would end up being a Phaeric victory for me. This is kind of outside of my uh, relevant, outside of this. These are kind of skills that I think aren't that relevant for me for what I'm doing, especially when you take a look at the other learning paths available on the site. I think I'm much better off spending the hours I would have spent troubleshooting to get this learning path to work, moving on to something like machine learning, working on the database one, although I had problems with that as well, going on the DevOps learning path. So I think continuing with the real Python tutorial is going to be a favorite victory for me if I can get it to work. So instead of that, we're going to move on. We're going to go right to chapter 12 in the book, which is container orchestration Kubernetes. I don't think finishing this book would be a favorite victory because just like in my mind, there's something about reading an entire book that kind of gives you more. It's kind of like affirming to me. It kind of helps my self-esteem to have finished a book, to just like read part of it and not and give it up. Even that's where especially since I can just skip sections, skim. I don't have to have every single word memorized, but to just give it up and not see what the rest of the book has. The last page could have the most valuable part of the book in it. So to skip it, or to read a book all the way from cover to cover, despite really not getting that much out of the book, um, I think isn't necessarily always a Pyrrhic victory. Um, and I think this is kind of a good. One of the commenters wanted me to continue on with this book, so thank you for that. Uh, Anyone watching this, if you leave a comment or something, I see them all because this channel is so small. So it really helps me out to kind of know what people will benefit from seeing. Now, I will say I can't always just jump to what a commenter wants me to do because I have my own goals. But I am definitely pretty flexible at this point. Okay, so yeah, we're just going to move on to chapter 12. So the name of this next uh, video that I'm going to post is going to be chapter 12, part 1. If you are experimenting with Docker, or if running a set of Docker containers on a single machine is all you need, then Docker and Docker Compose would be sufficient for your needs. However, as soon as you move from the number one single machine to the number two multiple machines, you need to start worrying about orchestrating the containers across the network. For production scenarios, this is a given. You need at least two machines to achieve default tolerance slash high availability. In our age of cloud computing, I turned the page by accident. The recommended way of scaling an infrastructure is out, also referred to as horizontal scalability, by adding more instances to your overall system, as opposed to the older way of scaling up, or vertical stability, by adding more CPUs and memory to a single instance. Okay, so let me break that down. And I think I'm going to highlight that too, because that's pretty valuable, I think, to have a good sense of. So I think I can just I thought I could right click on it. It looks like there might have been an update to this. Um, so I don't know how to. Oh, okay. So it looks like you just highlight it, and then okay. So yep, we're gonna highlight like that. And now this will show up uh, here. I can get rid of this bookmark. Okay, and then I think the bookmark was actually here. So I'll just add the same bookmark that I deleted, but now I know for sure that this page is the one that is bookmarked. So let me break this down just to make this extra super clear. I think it's clear enough, but I just want to make it extra clear. So here's your just this is representing like your regular system, whatever that happens to be. So in our age of cloud computing, the recommend so actually it's not going to represent, it's going to represent infrastructure. So this here is infrastructure. So I'll name it that. There we go. So that's what this square is representing, just your infrastructure. So in the age of cloud computing, our recommended way of scaling infrastructure is out, which is referred to as horizontal scalability, by adding more instances to your overall system, as opposed to the older way of scaling up, or vertical scalability, by adding more CPUs and memory to a single instance. So in the old way, you have your infrastructure, and then you have whatever instance you have in your infrastructure. I guess a good way to think about this. You can even think of it, I think, in terms of like your home network. So like I think like in the old days you would have, and if you're my age, I'm in my mid 30s. You might remember, gateways, Pentium 2, Pentium 1, Pentium 3. So what you would do is your family or your friend or whoever you know knew who could have computers like this. If it's yourself, then you'll definitely know what I'm talking about here. Like every year or every 2 years or every few years, and I think anyone who had a computer in the house can relate to this. uh, your computer would just be a brick. It would just suck. It would be slow. It wouldn't do what you wanted. And then the neighbor would have the newest computer, and they'd be playing, awesome games on it. They'd be doing really cool stuff with it, and you're stuck with this brick. So you have to go and throw that computer away, dispose of it somehow, bring it to like a recycling center or something, and buy a whole new computer. But at the end of the day, you would still just have that one computer. You would just have more RAM, more CPU, more storage power in that computer. Nowadays, when you buy a computer, I found your computer is like pretty like for me uh, like this computer here I bought like a long time ago, and it's like a Asus gaming PC, and like this has more like power than I ever need for anything. I actually decided to buy a new computer. The one I'm using now I can't pick up because it's a little bit fickle, just because this was too big and I wanted something smaller. And then I I used to do kind of a lot of, and I showed that on this channel too. I used to go back through my high school and middle school math education using Khan Academy and really bring that up to speed. So I wanted a stylus so I could write on a screen. So I bought a Samsung Galaxy Tab A. I wanted to play around with uh, like Raspberry Pi computers, so I bought some Raspberry Pis. I was kind of a Luddite holdout when it came to smartphones, but eventually I bought a smartphone and I have a smartphone. So you can see kind of the difference between the old school way where you would have a computer and all of a sudden your computer was a brick because new computers did all these cool things and you're stuck playing whatever DOS games you've always played, which are boring compared to the new games. So you just buy a new computer, and now your old computer is basically worthless, and it goes in the trash or wherever it ends up. But nowadays, it's completely different. You basically buy a computer based on what you need a computer for. If you need a phone, you buy a phone, which is a computer. If you need a desktop with a lot of power, you buy that. But even though you have a lot of CPU, RAM power in your gaming desktop, maybe you need to take a laptop with you on the road for whatever reason, or you want to do something uh, that's not in your house. So people have laptops, tablets, all sorts of different kinds of computers. They kind of scale out instead of scaling up. So I think that's kind of what they're saying here. That's a good way to kind of understand what that means if it's not clear. But that's not the whole story, because I think what they're talking about with orchestration and Kubernetes here is kind of getting all of those devices to interoperate. All right, so let's just continue reading. That whole diversion was probably unnecessary. I think it's clear enough what they mean with scaling up versus scaling out. But I just kind of wanted to bring that up because a lot of this stuff I think is really interesting because it's just so. It's not like learning something like history or some abstract concept. I think just because this is I think finding real world examples for this kind of stuff is a pretty easy task. All right, so a Docker orchestration platform uses these many instances or nodes as sources of raw resources, CPU, memory, network, that it then allocates to individual containers running within the platform. This ties into what we mentioned in chapter 11 in regards to the advantages of using containers over classic virtual machines. The raw resources at your disposal will be better utilized because containers can get to those resources allocated to them on a much more granular basis than VMs. Aha, I remember that. You will get more bang for your infrastructure buck. Yeah, I remember that. And I will, I'm going to highlight this. Yeah, because that's a really good summary of that. And then I'll do that explanation again. I think I did that in the video for chapter 10, but I just want to make that really clear. So with a VM, basically you have all of your resources available, but then when you build a VM, uh, let's say that your VM has to contain certain things. So basically you cut away a larger um, section of your available resources than if you were to just pin up a container. You can allocate your resources more intelligently, um, thus saving you more resources for later. So yeah, I think that's again pretty well written and self-explanatory. All right, so let's move on. There has been a shift from provisioning servers for specific purposes and running specific software packages on each instance, such as web server, cache software, database software, to provisioning them as generic units of resource allocation and running Docker containers on them, coordinated by a Docker orchestration platform. You may be familiar with the distinction between looking at servers as pets versus looking at them as cattle. I am not familiar with that distinction. Um, in the early days of infrastructure design, each server had a definite function, such as the mail server. And many times there was only one server for each specific function. There were naming schemes for such servers. Grigg remembers using a planetary system naming scheme in the .com days, and a lot of time was spent on their care and feeding, hence the pet designation. When configuration management tools such as Puppet, Chef, and Ansible burst onto the scene, it became easier to provision multiple servers of the same type, for example, a web server farm, at the same time by using an identical installation procedure on each server. This coincided with the rise of cloud computing and the concept of horizontal scalability mentioned previously, where you will take multiple instances and tie them together for more power instead of just loading up a single instance with more power. Kind of like the difference between like if you want to lift a car, you can try to lift the car, and if you can't lift the car, you can lift weights for a year, clean up your diet, and then try to lift the cart again, or you can get 10 buddies to try to lift the car with you. So obviously the better strategy is just getting help to lift the car. The Let me go back and read. This coincided with the rise of cloud computing, with the concept of horizontal scalability mentioned previously, and also with more concern for fault tolerance and high availability as critical properties of well-designed system infrastructure. The servers or cloud instances were considered cattle, disposable units which have more value in their aggregate. Damn, that's okay. But let's keep on focused here and let's not dwell on that last very upsetting statement. The age of containers and serverless computing also brought about another designation, insects. Indeed, one can look at the coming and going of containers as a potentially short existence, like an ephemeral insect. Functions as a service are even more fleeting than Docker containers, with a short but intense life coinciding with the duration of their call. In each case of containers, their ephemerality makes their orchestration and interoperability hard to achieve at a large scale. This is exactly the need that has been filled by container orchestration platforms. There used to be multiple Docker orchestration platforms to choose from, such as Mesosphere and Docker Swarm, but these days we can safely say that Kubernetes has won that game. The rest of the chapter is dedicated to a short overview of Kubernetes, followed by an example of running the same application, oh God, described in chapter 11 and porting it from a Docker slash compose to Kubernetes. We will also show how to use Helm, a Kubernetes package manager, to install packages called charts for monitoring and dashboarding tools Prometheus and Grafana, and how to customize these charts. Okay, so if they're going over the same thing, I might have to just skim through that again. But that's okay. I want to just get through this book as soon as possible because I just uh, honestly I'm a little bit disappointed with this book. Like um, it's just I think my time will be better. I think the best use of my time on this channel is focusing on RFCs. Because then you can share the knowledge, you can do that. So I wanna kind of get done with this book and move back to my wild networking series because that's where I read RFCs and do tutorials, and I kind of want to get into doing that instead of books. Short overview of Kubernetes concepts. The best starting point for understanding the many parts comprising a Kubernetes cluster is the official Kubernetes documentation. At a high level, a Kubernetes cluster consists of nodes that can be equated to servers, be they bare metal or virtual machines running in a cloud. Kubernetes run pods, or sorry, nodes run pods. Kubernetes is a uh, well, it's an application, I guess, a container management application. And then yeah, and okay, all right. There's a lot of okay. It seems like a lot of this language is really loaded here because we're starting here with a short overview of Kubernetes concepts. Okay, great. And then we're already starting in the first sentence. The best starting point for understanding the many parts comprising a Kubernetes cluster. So we were already introduced to the term cluster here, and that seems to be a really packed and loaded term uh, when it comes to how that is relevant to Kubernetes. So I think I'm gonna kind of try to just power through this, and if I want to come back and learn more about Kubernetes at some point, I'll just go straight to the Kubernetes documentation, and I'll make sure to make notes and highlights so I can come back to this book as well. Uh, okay, the other thing is uh, this word here, nodes. So at a high level, a Kubernetes cluster consists of nodes that can be equated to servers, be they bare metal or virtual machines running in a cloud. So this is also a really packed and loaded term um, that I'm just going to gloss over. And we can see how sophisticated of a term this is because nodes run pods, which also is a very uh, condensed word that means something. I think that is probably pretty complicated, which are collections of Docker containers. Yeah. A pod is a unit of deployment in Kubernetes. All containers in a pod share the same network and can refer to each other as if they were running on the same host. There are many situations in which it is advantageous to run more than one container in a pod. Typically, your application container runs as the main container in the pod, and if needed, you will run one or more so-called sidecar containers for functionality, such as logging or monitoring. One particular case of Sidecar containers is an init container, which is guaranteed to run first and can be used for housekeeping tasks, such as running database migrations. We'll explore this later in this chapter. An application will typically use more than one pod for fault tolerance and performance purposes. The Kubernetes object responsible for launching and maintaining the desired, I can't read and pour this at the same time, or maybe I can. I can. Number of pods is called a deployment. For pods to communicate with other pods, Kubernetes provides another kind of object called a service. Services are tied to deployments through selectors. Services are also exposed to external clients, either by exposing a node port. Sorry, no, I read that right. A node port as a static port on each Kubernetes node, or by creating a load balancer object that corresponds to an actual load balancer if it is supported by the cloud provider running the Kubernetes cluster. For managing sensitive information such as passwords, API keys, and other credentials, Kubernetes offers the secret object. We will see an example of using a secret for storing a database password. Okay, so this is using Compose to create Kubernetes manifests from Docker Compose dot YAML. Let's take another look at the Docker Compose.yaml file for the Flask example application discussed in chapter 11. Okay, so taking a look at that. All right. We will use a tool called Compose to translate this YAML file into a set of Kubernetes manifests. To get a new version of Compose on a Mac OS machine, first download it from the Git repository, then move it to the to that absolute path and make it executable. Note that if you rely on your operating system's package management system, for example, apt on Ubuntu systems or Yum on Red Hat systems, for installing Compose, you may get a much older version that may not be compatible with these instructions. Run the compose convert command to create the Kubernetes manifest files from the existing docker/compose.yaml file. So I'm not following along with these. I probably could at this point because I've got to a certain level in the tutorial where like these files exist, but I don't want to. I don't want this to just turn into hours and hours of troubleshooting like it did before. As I mentioned earlier, I just want to basically be done with this book and work through it as fast as I can. Deploying Kubernetes manifests to a local Kubernetes cluster based on Minikube. The next step is to deploy the Kubernetes manifest to a local Kubernetes cluster based on Minikube. Yeah, see, this is I I should just like this book is really frustrating me. Like I probably out of 5 stars, like I would have given this a pretty high rating near the end, but like this middle section, I would give this like a 2 out of 5 stars. I mean, that's just kind of frustrating to me um, that they have a title section that is called Deploying Kubernetes Manifest to a Local Kubernetes Structure Based on Minikube. And then the first sentence of that section is, our next step is to deploy the Kubernetes manifest to a local Kubernetes cluster based on Minikube. It's like just start that section with a prerequisite to running Minikube on like this whole thing, like to me it almost seems like it's padding where like the book just wasn't long enough, so they're just like adding in extra words. So that's really frustrating to me. A prerequisite to running Minikube on Mac OS is to install VirtualBox. Download the VirtualBox package for macOS from its download page and install it, and then move it to that path to make it executable. And that's a absolute path. It's not a relative path. At Note that at the time of this routing, Minikube installed a Kubernetes cluster with version 1.15. If you want to follow along with these examples, specify the version of Kubernetes you want to install with Minikube. Okay. The main command for interacting with a Kubernetes cluster is kubectl. Install kubectl on a Mac OS machine by downloading it from the release page, then moving it to that absolute path and making it executable. One of the main concepts you will use when running kubectl commands is context, which signifies a Kubernetes cluster that you want to interact with. The installation process for Minikube already created a context for us called Minikube. One way to point kubectl to a specific context is with the following command: kubectl config use context minikube switched to context minikube. A different and more handy way is to install the kubectx utility from the Git repository, then run this. Tip: another handy client utility for your Kubernetes work is kube-ps1 for a macOS setup based on ZSH. Add this snippet to the file. These lines change the shell prompt to show the current Kubernetes context and namespace. As you start interacting with multiple Kubernetes clusters, this will be a lifesaver for distinguishing between a production and a staging cluster. I think you can get ZSH if you're on Linux as well. I'm not sure. One of the things I want to do is switch this over to running Ubuntu instead of Linux, instead of Windows. Just get rid of Windows on it. Okay, so yeah, and then that'll make probably like following along with these examples a little bit easier because then I'm not doing it like on a VM or whatever. I'm just doing it on an actual like, and then I won't have all the lag and stuff when I'm using the VM. But it would be hard. I'd have to do like a remote desktop session or something. Now run kubectl commands against the local minikube cluster. For example, the kubectl get nodes command shows the nodes that are part of the cluster. In this case, there is only one node with the role of master. Start by creating the persistent volume claim PVC object from the file dbdata persistent volume claim.yaml that was created by Compose and which corresponds to the local volume allocated for the PostgreSQL database container when running it with Docker Compose. To create this object in Kubernetes, use the kubectl create command and specify the file name of the manifest with the -f flag. List all the PVCs with the kubectl get PVC command to verify that our PVC is there. The next step is to create the deployment object for PostgreSQL. Use the manifest file dbdeployment.yaml created previously by the Compose utility. To create the deployment, use the kubectl create-f command and point it to the manifest file. To verify that the deployment was created, list all deployments in the cluster and list the pods that were created as part of the deployment. Next, create the database for the example Flask application. Use a similar command to docker exec to run the psql command inside a running Docker container. The form of the command in the case of a Kubernetes cluster is kubectl exec. Yeah, and I think this kind of stuff like, oh, they're using 11.4 too. Was that what I was using? Like I think maybe some of the problems I was having, because this is where I was having like a lot of problems. Uh, but it might have been due to the fact that I was running it in GNS on a VM, you know, I'm trying to run like a VM in a VM in a VM. So like that's why I want to convert this over. I'll probably do that after this video. Um, I don't think I need to make that as part of this channel. Um, but yeah, I'll probably do that after this video. I want to put in some IESP off-camera study as well. So after this section, I think I'm done with this video. I'm not going to go too long on this. The next step is to create the service object corresponding to the DB deployment that will expose the deployment to the other services running inside the cluster, such as the Redis worker service and the main application service. Here's the manifest file for the DB service. One other thing to note is the following section, the label section, which we can see is here. So io.compose.service, and then it's set to DB. This section appears in both the deployment manifest and the service manifest, and is indeed the way to tie the two together. The service will be associated with any deployment that has the same label. Create the service object with the kubectl create-f command. List all services and notice that the DB service was created. The next service to deploy is Redis. Create the deployment and service objects based on the manifest files generated by Compose. Oh, that's interesting. They're using port 6379 as well. I was using that in the real Python tutorials. Kind of wish I had gone through this actually, because maybe it would work. But as I said, I don't want this to just be troubleshooting. So far, the two services that have been deployed, DB and Redis, are independent of each other. The next part of the application is the worker process, which needs to talk to both PostgreSQL and Redis. This is where the advantage of using Kubernetes services comes into play. The worker deployment can refer to the endpoints for PostgreSQL and Redis by using the service names. Kubernetes knows how to route the requests from the client, the containers running as part of the pods in the worker deployment, to the servers, the PostgreSQL and Redis containers running as part of the pods in the DB and Redis deployments, respectively. One of the environment variables used in the worker deployment is database URL. It contains the database password used by the application. The password should not be exposed in clear text in the deployment manifest file because this file needs to be checked into version control. Instead, create a Kubernetes secret object. First, encode the password string in database 64. Then create a manifest file describing the Kubernetes secret object that you want to create. Since the base64 encoding of the password is not secure, use SOPs to edit and save an encrypted manifest file secrets.yaml.enc. So we did that before in the example, got that to work. Really important thing to know, but I'm not going to do it again. It's I already did that before in chapter 11. Inside the editor, add these lines. The secrets.yaml.enc file can now be checked in because it contains the encrypted version of the base64 value of the password. To decrypt the file, use the sops-d command. Inspect the Kubernetes secrets and describe the secret that was created. To get the base64 encoded secret back, use that. To get the plain text work back, use the following on a Mac OS machine. Yet another reason I'm not doing these examples, I don't have a Mac. I do have a Linux VM, but again, I'm wondering if part of the reason this wasn't going so well for me is because I was using my Linux machine as a VM. But on a Linux machine, the proper flag for base64 decoding is -d, so the correct command would be that. The secret can now be used in the deployment manifest of the worker. Modify the worker-deployment.yaml file generated by the compose utility and add two environment variables. And before I begin, I'm serious about doing some off-camera JNCI ESP study. So I'm gonna, sorry, I guess I should pause the video to do this, but I'm just gonna start up my, I'm gonna trash one of my instances, one of my lab instances. It takes an hour and a half for it to start up, so I'm just gonna hit the start button on it now, and then at 4 o'clock, I think I'm gonna spend probably like 4 hours or at least on it. Sorry, I probably should have paused the video for this. I didn't think it was going to take this long. I thought I'd literally just have to click a button. Okay. All right. Okay, perfect. It's in setup mode now. Okay, so dbpass is the database password that will be retrieved from the fbe-secret file. Oh, okay, yeah, that's okay, perfect. Oh, well, it's an object. The database URL is the full database connection string for the PostgreSQL, which includes the database password and references it as this. This is the modified version of worker deployment HTML. So we modified it to take in, yep, here's the FBE secret file. So now we don't have any plain text passwords. Much more secure file this way. Create the worker deployment object in the same way as for other deployments by calling kubectl create-f. List the pods. Note that the worker pod is shown with status init. To see details about this status, run kubectl describe. Okay. The deployment tried to pull the Grig Gahio flash by example v1, and we got that working before. I kind of tempted to pull up my lab, but let's just keep on going. Private Docker image from Docker Hub, and it lacked the appropriate credentials to access the private Docker registry. Kubernetes includes a special type of object for this very scenario called an image pull secret. Create an encrypted file with SOPs connecting or containing the Docker Hub credentials and the call to kubectl create secrets. Okay, looks good to me. Decode the encrypted file with SOPs and run it through bash. The only change to the worker deployment manifest is to add these lines. Include it right after this line. Delete the worker deployment and recreate it. Now the worker pod is in a running state with no errors. Inspect the worker pod's logs with the kubectl logs command. The next step is to tackle the application deployment. When the application was deployed in a Docker Compose setup in Chapter 11, a separate Docker container was employed to run the migrations necessary to update the Flask database. This type of task is a good candidate for running as a sidecar container in the same pod as the main application container. The sidecar will be defined as a Kubernetes init container inside the application deployment manifest. This type of container is guaranteed to run inside the pod it belongs to before the start of the other containers included in the pod. Add this section to the app deployment.yaml manifest file that was generated by the Compose utility and delete the migrations deployment.yaml file. Reuse the fbe-secret object created for the worker deployment in the application deployment manifest. Oh my God. Yeah, so here's a good example here because this is the problem I had. So it looks like they don't have local hosts here. They just have the name of the database. The other really interesting thing to note is they only have two forward slashes instead of three. Create the application deployment with kubectl create-f and then list the pods and describe the application pod. The last piece in the deployment of the application to Minikube is to ensure that a Kubernetes service is created for the application and that it is declared as type load balancer so it can be accessed from outside the cluster. Note, similar to the DB service, the app service is tied to the app deployment through a label declaration that exists in both the deployment and the service manifest for the application. Create the service with kubectl create. This command, okay, and then the next step. So I think they're giving, yeah. So here's the command. Looks like there's more commands they want. Oh yeah, just to list out what the services are, and then Minikube service app. This command opens the default browser with the URL and shows the homepage of the Flask site. In our next section, we will take the same Kubernetes manifest files for our application and destroy them, or sorry, deploy them to a Kubernetes cluster that will be provisioned with Pulumi in the Google Cloud platform. Oh man. All right, so that's going to be it for this video. Yeah, I'm kind of as I've been saying, uh, every time I do this, I guess in one sense I'm glad because I'm almost done doing it, but I'm not sure how much I'm getting out of this, especially when there's just so much else I could be doing. It's limitless in tech. There's so many things I could be learning. We saw all those learning paths for real Python that were pretty much free to go through. I've got my other channels. I've got RFC or my other playlists. I've got RFCs, other books. So yeah, and then off camera JNCIESP retake. I honestly think I could pass that if I really put some effort into that. All right, but yep, that's it for this video. Thanks for watching and see you in the next one.